Good afternoon, students. Whether I am audible, whether slides are visible to you. Hello. Anyone can unmute and tell me whether my slides are visible.
Yes, sir.
Okay, ma. Thank you. Um, so last class in Unit 4, we have discussed about that memory technology. So basically, what are the two different types of technology available, like SRAM technology as well as DRAM technology? We have discussed in that. What is the features of SRAM technology as well as what will be the challenges in SRAM technology, and then what will be DRAM technology, what will be the features, and then how we are going to improve that DRAM, as well as what will be the dependability, all those things we have discussed. So for example, if you refer to SRAM, it is going to be SRAM is nothing but we call it as static RAM, DRAM is nothing but we call it as dynamic RAM, and then we discuss about how many transistors are used, like six transistors are used. Here we have only one transistor in DRAM. How we that is faster for in order to store single bit. If you refer to DRAM, little bit slow. Why? Because of we need some refreshing circuit charging mechanism is used. And then we have discussed about some different. We have asynchronous interfacing required to a memory controller. So we have used one clock cycle. Clock is used to cycling is used to every cycle. Sorry, every module. That way it is going to be called as SDRAM. And then we have DDRAM, double data rate. We have discussed how what is called as double data. For example, it is both rising edge as well as falling edge. We are going to transfer the data. Something, all those things we have discussed. I think this topic and all you are, it is clear for you. And then we have uploaded the video also in that class, both the classes. In that unit 4, we have discussed about, first we start with the 10 optimization technique, which is taken by Madam, and then followed by memory hierarchy, which is taken by myself, and then memory optimization technique also we have taken, that is going to be taken by myself. Next, we are going to discuss about that protection via virtual memory. Okay, so one more, I think one more topic is left out in this unit 4. Almost we are going to come to the end of this unit 4. Okay, soon we will complete the syllabus. I think you might have completed the exams also. So one more exams will be there in optimization. But sorry, 10 optimization technique. Soon we will have some announcement regarding the next exam. Okay, that is going to be the information I want to convey. So today we are going to discuss about protection via virtual memory. So the title is given as protection via virtual memory. How we are going to protect? So in that case, the answer is very simple. With the help of paging as well as segmentation, we are going to protect this virtual memory. So why we have to, the next question, how we are going to protect? That for that answer, we are going to use the technical paging, and then we are going to use the technical segmentation that will help you for order to protect the memory. The next question, that question will be asked, why we have to protect it? So in that case, you all know there will be something called as process. So normally process will be called it as that breathing as well as the heart of any program. So we have a process in each and every program. There will be so many process. So in that case, process has to utilize that memory as well as IO. Whenever the process is going to use that memory as well as IO, there will be some characteristics are going to be there. So either the processor will not use that memory as well as IO, or otherwise there is a process will be used affordable, not affordable, a portion of memory as well as IO, or otherwise it will use the entire memory as well as IO, which means that we have one system that there will be two important resources along with the process. One is going to be called as memory, one is going to be called as IO. So in that case, the process what we are going to use is going to use the memory fully or otherwise partially or otherwise completely. Without using that memory or IO, or otherwise partially it is going to use or otherwise. So in that case, for example, that process Why we are, that process is not only single, it is going to be a multiple process. So you all know that is that integrity, or otherwise we can say that multi-programming. So we are going to have multi-programming. So in that case, several programs runs. What is multi-programming? You know, several programs running concurrently. So in that case, it will share the computer according to the demands. So in that case, whenever we are going to share, that is the resources, we have to protect. There should be some protection has to be there. So why? Because for example, if I'm going to share, in that case, we have to protect. Otherwise, if there is any update or otherwise anything, I think it should not affect any other process. So that is why we are going to give protection. So we are not going to protect means we are not going to completely lock that from memory as well as IO without use by anybody else, which means that we are going to have some cover. So in that case, it should not affect any other process. That is why we are going to do some mechanism for a particular period of time. So we have some time. So in that case, that you all know there will be something called as interleaving concept. So this process will access this particular period of time. At that time, it will share this much amount and then this much amount of IO. So in that case, after that, it will be that information will be given to somebody else, or otherwise there should be a proper update has to be there. So in that case, so we have to have some. So we have to have some proper protection has to be done. So in this multi-programming environment. So after that, whenever we have a process, there is one more important information involved. The process going to be switched or process switching, or otherwise there will be something called as context switching is going to be done. What is basically process as well as context switching? Is nothing but you all know. So for example, just now I told you I will make use of some registers. There I will make use of memory. So we have something called as main memory. We have something called as register. So in a particular processor, we are going to use some set of register. Once the process gets over, we have to update that information to the main memory. So that is going to be called as process switch or context switching. We have to switch. So the process is going to switch. That the upgradation is going to be done to that main memory, vice versa. After, for example, if a register needs some information, it will take from that main memory and then it will make use of that one. That is going to be called as a process switch or otherwise context switch. Okay. That day, I got one feedback that you are going a little bit fast. So that time I have to complete. So today you have any that kind of feedback, you just tell now itself, you unmute and then tell me. I think and now I'm going correct. Okay. So now you have any doubt this process switch as well as context switch? You have any doubts? You can tell me. Any doubts? Shall we move further? Okay. So now in that case, I think there is no doubt at all according to that process switch. How the protection can be done? So that who are all the involved in this kind of protection is that operating system. So you all know there will be something called as OS in that system, and then we have something called as architecture. So it will jointly put together, and then it will force us to allow that process to share the hardware. So in that case, this particular architecture and then operating system put together to share the hardware, but it should not be interfered with each other, which means that one process will share something, but it should not be interfered by some other process. That is going to be. So in that case, this operating system as well as architecture will have much care in order to protect that particular. So at the minimum point, architecture has to follow some such of things. So some sort of thing has to be followed by that architecture. So in that case, we are going to use, that architecture will provide at least two modes of operation. There will be something called a user mode, or otherwise will be called as less privileged mode, or otherwise we are going to have something called as kernel mode or supervisor mode. So already the user mode, just now I told you that will be called as less privilege mode. Something will you can ask, there will be something called as either it is having any high privilege mode. Yes, we have high privilege mode. So we have high privilege. So we have some set of instructions. User mode, we have some less privilege, and then we have something called as higher privilege. So in that case, some sort of process will be in higher privilege. So in that case, straight away, I can't use that higher privilege level instruction in that lower level itself. So in that case, what I have to do is I have to move on to the kernel mode or supervisor mode, and then there I can execute that kind of process. So in that case, what it will means, so what is the ultimate aim? That architecture will have supervisor mode, it will have full control. Whereas in case of, for example, user mode, there is no full control at all. So that is going to be called as least privilege. So either it will process and then it will update themselves. So normally we will say whether we have a read access, whether we have a write access, something like that. So that is going to be called as privilege. And then that architecture also much care about, it provide a portion of process that user process can use but not write. So that's why just now I told you. So I have some portion of memory, I can use it for my process. I will read some information from the main memory I want to utilize, but I should not update that any information to that main memory. So that is why I can utilize that memory portion for a particular process. So in that case, I can read and then I can utilize. So that is going to be called it as a portion of memory will be read, it cannot be write. So there will be avoid user process gain control or void memory protection. So we have some gain control. So that's what I told you. We have user process gain control. So it will take gain control, which means that at a particular period of time, it will get the overall access, and then it is going to be a void, and then it will be fully protected. So it is just not possible to modify it. Architecture also, whereby that it will go from user mode to supervisor mode, or otherwise vice versa. So which means that sometimes I need to some sort of process has to be, you all know there will be in particular application there will be so many processes. In particular position I have to go from switch over from user mode to in that case system. So at that time that system call will be used. What happens, that system call, it will save the current context into the program counter, whatever that program counter, it will hold the it will, what will be the current address, it will be stored in that stack. After that for example, it will jump to a particular place there, this kind of for example, what we can say, this high privilege thing will be process will be carried out. After that it will be come back to again to that lower level, less privilege level, and then it will receive that process. So for that we are going to use something called a system call. The system call is used for switching from lower level, or otherwise we call it as less privilege level, or otherwise we call it as user level to supervisor level. And then from once process gets over in supervisor level, again we can come back to this user level. Okay, so this process is possible. This kind of things can all carried out by that special care can be, the special care will be taken by the architecture in order to perform. And then there will be some mechanism to limit the memory access to protect the memory state of a process. So without having to spare the process to disk or context switch. So we have to protect. So we have a, so for example, this particular portion alone, you are eligible to use. So for example, instead of swapping the process from disk or otherwise, which means that disk is nothing but what we have called as main memory. So we have something called as virtual memory, no? So we have virtual memory and then we have a disk, something like that. So in that case, there should not be context switch. So which means that, so we have this much amount of memory you can utilize, and then whatever things you want to do, you can complete within this memory. So this will avoid unnecessary context switching between from virtual memory to main memory or virtual memory. That is called a secondary memory, something like that. I think I have clearly explained about why we need protection, how protection can be done. So these are all the basic questions. So how the protection can be done is basically with the help of paging and then segmentation. why we have to go for this kind of protection? So we have to avoid any interference between multiple processes. So just now I told you there is something called as paging. So paging, you all know. So just this is the overall diagram. We will call it as virtual address. So paging is nothing but we are going to have some virtual address, virtual memory, paging, and then physical address means we will call it as main memory. So that is the difference. So in that case, you have a virtual memory, that size is going to be the same as your main memory. So in that case, whatever the blocks we are going to have in virtual memory, that is going to be called as pages. So we are going to call it as pages, whereas in case of physical memory, we are going to call it as frames. Okay, so that is one important information. And then it is going to be that reallocation. So we have something called as, for example, reallocation. Something is not available. So in that case, we have to reallocate. So virtual memory, I will check for with the main memory. If it is not available, I will check with the virtual memory, and then we are going to have the reallocation. So in that case, one important thing you have to keep it in mind. So the processor point of view, it will think only about main memory. So whatever that process I want to do, that has to be kept in that main memory. From there only it can be possible to execute. So in that case, for example, if I want to search for a particular memory reference, so you have, for example, we have a page number, and then already I told you that the pages which will be equal size, we have a page number, and then the size is going to be equally distributed. Whenever we are going to think about paging, we are not thinking about discussion about segmentation. So we have segmentation is the entire thing. So we have to have some frames, we have to have some pages. So in that case, we have we have equal size. So in that case, if I will check for a particular reference, so if it is not available, which means that there will be a page fault will occur. So in that case, we have to take from that virtual memory to that we have to keep it that we have to get the data from virtual memory, and then it has to be here. But immediately straight away it is not possible. First we have to have some page translation, which means that so the virtual memory address has to be converted into physical memory address, then only it is possible. That is why we have some virtual addresses, we have to have physical address. So memory mapping or address translation has to be done. So for example, if you refer to this particular diagram, so we have virtual memory. So we have that process A, B, C, D, all those things are going to be in that virtual address. So already we have that process, and that is why reallocation, relocation. So we are, for example, if that virtual address is going to be 0 to 3K, 4K, whereas in case of here it is going to be in 16K. So in that case, we are going to reallocate wherever it is available, memory is possible, and then we are going to keep that thing. So in that case, whenever the processor going to think about the process A, it will take straight away physical memory, and then we take B, C, something like that. But whenever coming to the process D, it is not available. So that is not available disk. So which means that it is going to be in the secondary memory. So in that case, what it has to immediately page fault will occur. So in that page fault occurs, once page fault occurs, we have to check for that disk. So in that case, we have to convert that physical memory to virtual memory to physical memory. The translation has to be done, and then it has to be taken. So this is one kind of thing. So this is called as paging. So with the help of paging, we are going to have. So for this, we have something called as page table, page directory, all those things is there. For that detailed information and all, you have to study it separate concept. So what exactly, how that virtual memory will be helpful for in order to make use of that process, we have discussed in this particular slide. So whenever we are talking about main memory and secondary memory, it will be is a part of virtual memory. Secondary main memory, and then secondary memory will be a part of virtual memory. So whenever we are talking about secondary memory, is that hard disk that is going to be called as virtual memory. But the cache does not play any role in virtual memory. The cache is separate, and then secondary storage is separate, main memory is separate. So already we have discussed, we have something called as registers, we have something called as local memory, that is going to be called as cache, and then we have something called as main memory. So here you should not confuse with what that cache versus secondary. Cache is entirely different. There are difference between caches and virtual memory. So for example, we have something called as replacement on cache, which is primarily controlled by hardware. So you all know there will be something, already we have discussed something about miss penalty, miss rate or something like that. So whenever there is going to be there is a particular hardware which is used, so whenever we are going to have any cache miss occurs, that is going to be done by something called as already you all know there will be some hardware based snooping based protocol or otherwise directory based hardware protocol. These are all the two hardware, so just used by any processor for in order to carry out that kind of cache misses on there. So here this data miss is going to be done with the help of that replacement policies, whereas in case of here we are going to have something called as cache controller. We have something called as cache controller that is going to be a specific hardware that can also carried out by any protocol like snooping or directory based protocol, which is used for this kind of cache misses. Okay, so whereas in virtual memory replacement is primarily controlled by operating system. So that is the main information. So we have a virtual memory. If there is any replacement, so if there is any miss occurs, data miss occurs, that is going to be primarily carried out by control system. So sorry, not control system, operating system. So we have virtual memory replacement. So the disk, the previous example, the process D is stored in, for example, it is going to be stored in a virtual memory. Whenever the process miss occurs, immediately that operating system has to take care of to replace that from virtual memory, the data transfer, virtual memory address to physical memory translation, all those things will be carried out by the operating system. So the size of the processor address determines the size of the virtual memory. The size of the processor address. So what will be the size? Everything has to be fixed. So that's why I told you. But whereas in case of cache, so the cache is going to be in minimum, and this was that will be some extent. So you have something called as some KB2 maximum, some MB or otherwise some GB. Whereas here that is going to be the secondary storage is going to be 1 TB or something like that. But the cache size is independent of that processor address size. So that size of the processor determines the size. So we can have, for example, if I am going to have 1 TB, the same I can have it for virtual memory. But whereas in case is independent of processors address size. So why I'm going to say is that means cache will be frequently used. That is why we are going to use cache is going to be limited. That is why if the cache size is going to be minimum, that miss rate is also going to be minimum. That and all we have discussed in the previous class. Okay. Now coming to this next in concepts, virtual memory system can be categorized into two classes. So already I told you there will be something called as pages, there will be something called as segments. So in that leftmost part, you have some diagram. So there will be something called as code, something called as data, something like that. If you refer to that page, that is equal in size. Wherever the code as well as data, the pages, the individual page size is going to be, for example, it is going to be in equal size. Whereas in segmentation, it is going to be in various size of blocks called segments. So we have a fixed size blocks called pages. Whereas in case of segments, it is going to be in variable size. So that information you have to impart. So this is one difference between segmentation versus pages. So we are going to have comparison. Well, which one will be efficient, or otherwise which one will be more comfortable. Not only we are going to say efficient, which one is going to be comfortable. And we have some comparison. So here we have some pages, we have segment, we have some attributes, word per address. We have word per address. So we have one page. So we have one block that will have one word. Whereas in case of a segment, we will have two things. One is going to be called a segment as well as offset. So segment, segment as well offset is nothing but the base value. So offset will have some value, and then segment will have the segment number. So we have page number, there will be segment number, that will be combinedly for in order to get the address. Now next the next slide I will tell you how to calculate the address on those things. So here 1 per word, here 2 per word. That is the information first you have to. So programmer is invisible to application programmer, may be visible to application programmer. What is basically invisible? For example, what we can program that page can be visible. So the segmentation is not visible. So may be visible to application programmer, invisible, sorry, application, sorry, this I get some confused. It is the page size, page and all, it is not invisible. Invisible to application programmer, whereas in case of visible to application. So, for example, there will be something called as replacing of block. What is meant by replacement? So, what is replacement? For example, all the blocks are same in size. So, which means that, for example, if a particular block is not used, so in that case, that memory, main memory, as well as that, for example, what we can say that paging. In that page that equal size. For example, here we have the page size is going to be 2K. The memory also we have a 2K size. That case, that portion is going to be equally we are going to replace. Whereas in case of difficult, why? Because we have to find out where exactly, because it is going to be in variable size. So you have to check for where equal size. You have to find out. After that, we have to that should be also unused, and then we have to map. That is going to be called it as replacing of balls is easy as well as difficult. So for example, we will check easily. So this particular 2K is not used, unused. So here I easily map, but we have to check. This is for example 1K or something like that. So in that case, in that also whether it is used, whether unused or something like that. Memory used in internal fragmentation. So, for example, what is meant by internal fragmentation, external fragmentation? What is basically internal fragmentation means? For example, if we have a 4K page size, so in that case, if you have used only 1K, the remaining time can be you can use it for some other purpose. That is going to be called as internal fragmentation. Whereas in case of external fragmentation, unused piece of main memory. So first, we have to think about where. For example, what will be the size? So we should not easily map it. So we have to check for what will be the size, and then which in that size also which portion is not used. We have to take. That is why we go for external fragmentation. So that is going to be there. And then, for example, efficient disk adjust the page size to balance the access time as well as transfer time. So, for example, adjust the page size. So, for example, what it is means we have equal size. So in that case, the transfer rate is going to be uniform. So for example, you have 2K. That transfer rate is going to be what will be the use. According to that, we will fix this is going to be the transfer rate. That is going to be adjust the page size and then balance the access time. So only 1K is used. So we can fix that. So same access time will be used. Whereas in case of not always, so transfer, for example, few bytes to max. For example, one particular segment is going to be different size. Another segment is going to be different size. You cannot follow uniform transfer rate. So here everything is going to be fixed 1K. Means transfer rate is going to be 1 kbps. Whereas in case of this segment is in different page, different size. So we should not follow uniformity. So this and all, there will be a small comparison between page as well as segment. So according to the situation, according to that requirement, you can use whether I will go for page as well as segment. So far what we have discussed is what is the difference between paging as well as segments. So for example, if it is question will be asked, where can a block be placed in memory? Where can a block be placed in a main memory? So, for example, we can place it in we can place it in a for example, virtual memory. So where we can be placed in a memory. So there will be something called as miss penalty occurs. So for example, if it is not available, automatically miss penalty over, we have to have the translation. How is a block is found if it is in main memory? So I have to refer with that page number. So we have a page number, and then we have a page directory, So, and then we have a page table entry cell there. So with that case, we have some offset. So with that, for example, I told you, we have a page number, we have a page offset that is going to be given from the virtual address. From that, we can convert that physical address. So the virtual page number, it will refer to the page table entry. After getting that value, that is going to be added with that offset. After that, we will get the physical address that is going to be converted into physical address. Then we can make use of that main memory. So this is that how it is, how I can make use of that main memory, something like that. So if which block should be replaced on a virtual memory? So whenever there is, for example, whenever there is we have something called as reference bit. So for example, periodically, if I want to use a particular memory block, so in that case, I will have some reference bit. If that particular page will have the value 1, so in that case, it is periodically used. So in that case, I can kept into that main memory. That is going to be which block should be placed on a virtual memory, which block should be replaced on a virtual memory. So that is the answer. So we have some reference bit. So based on that, I can put this kind of things will be this and all frequency used. So the case I can put it into that main memory. Something will be kept in a virtual memory. So in that case, I can avoid miss penalty, something like that. What happens on a write? So what happens on a write? Write strategy is write back. So you all know there will be something called as a write through and then write back or something like that. So what it will have? So for example, if I have something on that main memory, so in that case I have some computation. So in that case, what happens if after computation, if there is any update, sometimes write back, write through something. What will be the difference? You all know. So I will update it to the secondary memory, or otherwise I will not update it to the secondary memory. Okay, so that is going to be called as what happens on a write. So there are two policies available. So one will update, one will not update. So that is going to be called as write strategy in write back, and then write back, and then write through. So what it will be called as techniques for fast address translation. So fast address, just now I told you, according to the reference bit, some pages will be frequently used. So in that case, I can make use of this. For example, I will convert that into that particular pages, and then I will put it to that translation look at buffer, translation look ahead buffer. So in that case, there will be kept in this kind of pages. So immediately, again, if there is requirement, immediately I will put it into the main memory. So that is going to be a technique called the fast address translation. So already, for example, already this set of pages will be frequently used. So we have some reference. According to that pages physical address can be converted. That address and all I have to put it into the translation look at buffer. So immediately, if there is any miss penalty occurs, that will be immediately that pages will be mapped. So how to select a page size? So we have that page table is inversely proportional to the page size. So page table, so we are going to be a lot of entry that is going to be inversely proportional to what will be the page size. So page size is going to be 1K, 2K something. That is why it is going to be inversely. A larger page size can allow larger catches with fast catch hit. So for example, larger page size can allow larger catches. So for example, if I want to have, I will put the catch, and then I can make use of, I can avoid catch hit. So transferring largest pages from secondary storage possibly over a network is more efficient than transferring the small pages. So this and all straight away, straightly you can get. So and then I told you translation look at buffer entry is restricted. So it should be even though we have it is a fast data translation, I should not put more a number of pages. So I have to restrict to some page size. So which one is more requirement according to that particular process? According to that, I will keep all those things in this memory map. So how to protecting that process? So we are going to how we are going to protecting that process. For example, we have something called as presence. So says that present says that present says that page is present in a memory or not. So whether presence will say whether A is present, B is present, or D is present. If it is not there, so for example, 1 means that page is present. If 0 means that page is not present, so in that case, it has to look for virtual memory. So read write says whether page is read only or read write. So that value will be that again it will be 0 or 1. 0 means only read operation, 1 means write operation. So for example, you have something called as user versus supervisor, says whether the user can access the page or if it is limited to the upper 3 privilege levels. So we have already I told you there will be some 3 upper. So we have user level, and then we have a supervisory control, and then we have for example higher privilege level, something like that. So that is going to be called a super, says whether the user can access the page if it is limited to upper 3 privilege levels, like that. Okay, so you have any doubts so far? So far you have any doubts? Any particular point I want to recall, something like that, you tell me. Just simply I'm going, I want to complete that portions, that is why simply I'm moving little bit. I think if you feel little bit fast, I will start. Any particular thing I want to repeat, just tell me. Anyone unmute, or otherwise I like proceed. Shall I proceed? Hello, anyone can unmute and then tell me any doubts you have. Shall I proceed? Hello, I don't know how many of them online, whether you are just hello, can anyone and then unmute and tell me? Shall I proceed?
Yes, sir.
So whether you understand concepts, I think almost what are the things we are referred, everything is same as that previous continuation. Okay, now I will tell you the dirty. So you all know what is meant by dirty bit. So if a particular already told there will be something, we have a process, it will do some computation. After computation, for example, there will be something has to be updated. So in that case, we have something called as dirty bit. So in that case, that exclusive state. So which means that if the dirty bit is set to a particular page, in that case, it has to, that information has to be sent, and then everyone has to get the new data. So that is why it says the page has been modified. So that particular page has been modified. So it has to be informed, and then inform has to be informed. According to that, the remaining pages has to get updated information. So that is going, it is called as dirty bit. Accessed, say if the page has been read or written since the bit was last cleared. So continuous list, for example, how last accessed. So in that case, this is based, this particular page is going to be has been read or written, that is going to be checked. If it is not accessed, that it has to be cleared. So what it has means, if it is periodically, I will have to check for that particular bit is 0. So in that case, that particular page has to be removed. That is why it is going to be called as an access. Why I have to check for this particular means, if it is cleared means, if periodically I'm going to check for that particular page. So it will always, the value is 0. So which means that no process use this particular page. So in that case, that has to be removed. That has to be removed from the particular page. Whatever the thing has to be removed, and then it has to be utilized by some other process. So page size, whether the last level is 4 KB page or 4 MB page, if it is later than after, use through instead of 4 levels operator. So for example, page size is going to be fixed by that optron. What will be the size, whether I have to fix for 4K, whether I have to fix for 4A, depends on this operating system will take care of all those things. So no execute, not found in protection scheme. This may added to prevent the code for executing in some pages, which means that, for example, this and all, and this kind of protection will start from 386 onwards. There will be some bit is going to be added. So to prevent the code, so already I told you that will something called as critical code. So which means that it should not be interrupted by any other process. So we have some set of code that is going to be taken care. That should not be accessed by anybody else. No interruption should be that particular process. So in that case, we are going to, so for example, in that case, that particular portion has to be prevented. That is going to be called as no execute. And then we have something called as page level catch disabled. So whether the page can be catched or not, that particular memory can be catched or not. So that also whether we have some disabled. So if it is 0, that particular page can be catched. If it is 1, that particular page cannot be catched, something like that. So all these things are, these are all the steps to be followed for in order to protect a particular memory. And then page level write through. Already I told you, say whether page allow the write back or write through for data catches. So you all know, again, repeatedly, I don't want to say the same information, whether we have to do update or otherwise we are not going to update. So for example, how we are going to protection via virtual machine. So first, it will be developed in 1960s and all, only this kind of virtual machine concepts come to existence and then remain important a part of mainframe computing over the years. So today, this virtual memory concepts and all very important. So recently it gained more popularity. So why it is get popularity is that increasing importance of isolation. So which means that, for example, some portion will not be used, some process should not interfere, something like that. And then we have to have some security in modern system. So we have to protect, there needs some protection. So in that case, this kind of virtual memory concept comes into picture. The next one is there is a failure in securities. So and the reliability of standard operating system. So some, for example, there will be something due to some cyber crime. So cyber crime is going to happen, and there will be some reliability. So over that standard operating system. So this kind of virtual means comes to designer point of view. The next one is sharing of single computer among many unrelated users. So for example, so many users, that's why I told you multiple programming. So in that case, we need nowadays people are using data center, cloud or something like that. So private. So nowadays it is open to all. So in that case, we need some protection. And then dramatic increase in raw speed of processor, high performance processor, and then which make that overhead of virtual memory more acceptable. So these are all the need for very virtual memory is important. So in that case, how this virtual memory is going to be work? So virtual memory supports both that instruction set architecture is an underlying hardware. However, it is also possible to support different ISA. So we have x86 architecture, or otherwise we have something called a GPU, or there is virtual. For example, you all know we have different set of architecture. So that virtual memory, it will support both x86 architecture or otherwise any other instruction set architecture. It has to be support. Often employed when migrating from instruction set architecture such as support. So if I want to switch over from for example x86 to ARM architecture, ARM to migrating, that possible, also possible. So if a single computer runs run multiple virtual machines and can support a number of different operating systems, just to operating system also. So if I am going to have Linux, I have some Mac OS, and then I have some iOS, something like that. So in that case, if that is possible, that virtual machine can be an underlying architecture, it won't bother. That's all. Whatever that operating system, that virtual memory, virtual machines can support. So in that case, on a conventional platform, single OS, all the hardware resources, but with the virtual memory, multiple, all the hardware resources. That is the problem. So nowhere there will be some issues. So nowadays people are using, for example, Docker containerization. So whatever the basic platform, so it will have some images. So I have Windows platform that will be run on the top of the layer. So that will be that Linux. We have some whatever the requirement for this particular hardware, that will be converted as a machine images. So in that case, that can run in that way. So that is why it is whatever we will have something called as heterogeneous. So we are not bothered about nowadays homogeneous. We are bothered about we don't need to bother about the heterogeneous platform. So this how that software support virtual with the help of virtual machine monitor VMM. We'll call it as VMM, virtual machine monitor, or otherwise we'll have software hypervisor. So VMM is much smaller than traditional OS. So there will be something called as monitor, so that it will take care of all kind of protection, all those things. Okay, so in that case, for example, two benefits with the help of virtual memory, virtual machine monitor is going to be managing that software as well as hardware. So we have something called as legacy software. So that is going to be managed by this virtual machine. So this which VMM can take care of whatever the software available, whatever the hardware legacy available, it will take care of this. Even for example, we have some guest software. So what we can, if you want to run on the native hardware, it is possible. So we are not bothered about whether it will run or not. Simply we given to that VMM, it will take care of all those things. So in terms of, for example, whether it is going to be a real one or virtual or otherwise it is going to be a main memory, main whatever thing. So whatever translation, all those things will be taken care of. The chain allocation of real system. So virtual system, we have a main actual system, whatever that actual translation has been done. So that is why at least two processor mode, whether we have in system mode or otherwise user mode. We have a less privilege or higher privilege. All those things will be taken care by this VM. So what will be the impact of virtual machine on virtual memory and load? So that if there is one important challenge in virtualization of virtual memory, each guest OS in every virtual machine own set of page table. That is one important. So we have page table. That page translation is a very important thing. So we have some page table, page directory. So that offset. So in that case, virtual memory separate the notation of real as well as virtual memory. So that there will be, for example, we need some intermediate level. There will be some latency time to translate from one thing to one set of address to one address. So rather than pay an extra level of indirection on every memory access, so which means that, so for example, we have some real memory. Actually, we have some, for example, virtual memory. So immediately that real memory will that will be taken care by that address translation and all easily. So that case, we have for that we are going to have something called a shadow page table. So what is shadow page table? It is also similar to your translation lookup buffer. So we have some page table, shadow page table. So in that case, whatever that frequently required, that is going to be mapped immediately for in order to complete that process. So these are all the impact of virtual memory machines and then virtual memory IOs. Okay, so that is going to be the end. This is going to be the end related to virtual memory as well as memory protection over the virtual memory. Okay, so with this I will stop. I can share this video. You can go through, and then if you have any doubts, already I told you several times, you can ask me later point. Okay, so now
sir, please post the PPTs in our classroom also, sir. Azil ma'am classroom.
Yeah, PPT. Okay, definitely I will. So what I have think is I consolidated and no problem. Now itself today itself I have put all that PPTs in that madam classroom also. Already I have put in the video and then now I will complete. Put that up to virtual machines. And then Manoj, the TSV, you have asked about one doubt regarding what is loosely coupled, tightly coupled. I think so. That GCR you have put. Loosely coupled, tightly coupled means, for example, that architecture itself predetermined. So this many device can be integrated. For example, tightly coupled. This example, if you refer to your laptop, you have some ports, I/O ports. So in that case, it is tightly coupled. Maximum 6 ports. So in that case, already if it is filled, so in that case, it is not possible during runtime. It is not possible to add. So that is going to be called as tightly coupled. Loosely coupled means anytime if you are dynamically, you can integrate. So not only for hardware, any set of operations. That is going to be called as loosely coupled system. Okay. Manoj TSV, I think clarified your doubts. Still you have any doubts, you can ask me now. Any other thing?